Hey, good morning, chemistry team. We're going to look at a special type of atomic solid today, network covalent solids. And I briefly mentioned this when we did the video on solid types. So we looked at ionic solids, particles or ions, molecular solids, particles or molecules, and atomic solids, particles or atoms. Don't overcomplicate chemistry, my friends. And that was just kind of a brief introduction. So we spent a couple videos on ionic solids, right? Last one on Born-Haber diagrams, the Born-Haber cycle, all that fun stuff, lattice energy. I'm not going to do a separate video on molecular solids because you just got the molecules, right? And they're going to have some kind of intermolecular force between them, which is going to be weaker than ionic forces. So, they'll have, if they're nonpolar, all London dispersion forces, water has hydrogen bonding plus some LDF. You might have dipole-dipole plus LDF. So, but much weaker than ionic solids. So they have a lot lower melting points, really impacts those properties, tend to be more gases or liquids at room temperature. Unless they're really big and have stronger London dispersion forces, they might be a solid at room temperature. So we won't do a separate video on molecular solids. But atomic solids, we're going to do a couple videos here. We mentioned you could have like noble gas solids, which fall in the same category here, where you've just got noble gas atoms with weak London dispersion forces, super low melting points, boiling points, etc., etc. We're not going to do a video on that. But I did mention network covalent solids and metallic solids. So I'm going to do network covalent solids as one of the subcategories of atomic solids in this kind of quicker video. It's kind of fun. You probably learned this stuff already in introductory chemistry, I would imagine. So we'll just go through it again. It's kind of fun, good fun applications. And then we'll finish up solids looking at the special type of atomic solid, metallic solids, and crystal structures through closest packing, FCC, BCC. We'll get into that kind of stuff later. So let's take a look here. Not many examples of this, but they're pretty common in your everyday life. My guess is, as a student, you use one every single day. So network covalent solids, here's the word, covalent, like covalent bonds, right? Super strong bonds there. So these are special class of atomic solids where you've got some atoms, that's why it's an atomic solid. But instead of like noble gas atoms, we've got these weak London dispersion forces between them. Boom, you lock in and share electrons and form a covalent bond, right? Not many atoms can do this over an extended array, right? A lot of them can do that, chlorine molecules can form a covalent bond, but then you just have a diatomic chlorine molecule and it's a molecular solid, and the forces of attraction between two separate chlorine molecules are weak London dispersion forces. But things like carbon, right? Certain allotropes of carbon. If you're not familiar with the term allotrope, it's just different forms of the same element. So carbon we'll look at, graphite, diamond, buckyballs, there's carbon nanotubes, all these different forms of carbon. Some of them function as network covalent solids, where you have the carbon atoms connected with a strong covalent bond by sharing electrons, and that continues over a three-dimensional lattice, essentially forming a gigantic molecule, right? Well, graphite's it's obviously slightly different, but in a similar fashion, we can call that a network covalent solid. And some silicon compounds, more geology than I want to go, but I'll talk about. My son is a mineral collector, so things like quartz, right? Silicon dioxide functions as a network covalent solid. Not quite as beautiful as diamond, but we'll briefly mention it. So let's go, now that you have the basic idea, it functions as one gigantic network with covalent bonds. Well, that's going to really change its properties because covalent bonds are stronger than intermolecular forces. So you're going to see these melting points jack up, solubilities decrease, or just go away completely, as in the case of diamond. So let's go through. Let's look at carbon first. Your prototypical network covalent solid would be, if you have a diamond ring, take a look at your diamond real quick. All right, you ready to try to draw this? This is hard to do on a two-dimensional surface because it's a three-dimensional species, right? So we've got carbon atoms forming covalent bonds with overlap of sp3 hybrid orbitals, and this will form tetrahedrons. So here's your carbon, likes your 4 bonds, right? So let's just start with the central carbon. Draw that tetrahedron, and remember from first semester of general chemistry. And then you'll have carbon atoms. So we're doing kind of a dash wedge structure there. And then this carbon will be the top of another tetrahedron. So we can draw another tetrahedron like this. Can you see how this is going to get messy real fast? and put carbon atoms here and here. This one is the top of a tetrahedron here. And this one's the top of a tetrahedron here. So we can draw, you know, dashes and wedges. This is going to get crazy. Good luck with this, my friends. Right? This is the top of a tetrahedron. Right? You're going to have the dash wedge structure. So I'm getting a little turned around here. My angles are all off. But you get the idea. It's hard to draw on it. You get the idea. It's hard to draw on a two-dimensional surface. So it just, and that just continues in 3 dimensions. Not fun to draw on a two-dimensional surface. We all agree? So models help. Yay! So here's what diamond would actually look like on an atomic scale. I don't know if you can zoom in. Let's take a look here. Let me move this tag out of the way. Ugh. And let's focus right in here. Can you see that central carbon atom right here? Right there. Can you see that one there? That one up, line. There's your dash. Ooh, it's hard to see. Here's your wedge here, coming up front. So if you stare in there, you can see that. Oh, there it is. There's that beautiful, here's the center of the tetrahedron. Oh, I can't reach it. There it is. There's your central atom of that tetrahedron with one up, dash and wedge, one over. And you just repeat that over a 3-dimensional matrix. That's diamond. So that's going to create a really, really hard substance, because good luck trying to break these covalent bonds. Good luck trying to melt that or boil that. Super high melting point, super hard. So, and all the bonds are localized here. All the electrons are stuck in these bonds, so they're not free to flow. So this is an insulator. It is not a conductor of electricity, all these interesting things. So let me list a few of those up here real quick, and then we'll look at how different graphite is from this. All right, kind of mentioned this, and you probably already know this stuff. I mean, since you were a kid, you probably knew diamond is the hardest substance on the planet because you've got these really strong covalent bonds, right? Good luck with that. So it should be able to scratch anything else, and nothing can scratch it. Going to make some good industrial uses, right? So think about it. Right? If that's the hardest known substance, wouldn't that be a good idea if you're like trying to drill through metal or polish hard metals or something like that? Maybe use diamond in your polishing or in cutting, like in a diamond tipped saw, or crush up diamond and blend it in there, for the tip of a drill bit. Hey, that would make sense, right? I remember I was doing when I was working on my PhD, one of the proposals I had to do for my orals examinations, I looked at titanium vanadium alloys used for like hip replacements and things like that. To make them more biocompatible, I talked about using a diamond coating and forming a diamond coating on it by ion implantation. So it wasn't my research, it was just a fun proposal I'd looked at. But I looked at diamond coatings, biocompatible. It's kind of neat. If you're into geology and that sort of stuff, you have familiar with the Mohs scale, the hardness scale of 1 to 10. Talc being the wimpiest of the wimps at a 1, diamond being the toughest of the tough at 10, because of its covalent bonding as a network covalent solid. It's just fascinating, right? Another interesting thing is obviously its melting point is going to be huge. You're not breaking any intermolecular forces because it's all covalent bonds, super strong covalent bonds. So it's way up there with a lot of ionic solids too. It's probably over, it's hard to pin down a specific melting point, but it's in the 4,000 degrees Celsius range plus. It's a little tricky because remember phase diagrams, it can be pressure dependent. So this only occurs at really high pressure. If you're at 1 atmosphere and you're heating it up, it actually will sublime, right? I think it might even turn to graphite or something like that. So you got to get it to high pressure and then super high temperatures, man. Good luck trying to melt diamond. And because of those sp3 hybrid orbitals, all the bonding electrons are trapped in between the carbons. They're localized, so they don't move around. So if you jack an electrical circuit, an electrical current into it, it is not going anywhere. It's an insulator, so it's a non-conductor. And you can see this. There was I can't remember. There was a show. There was some superhero named Translucent or something like that. And they kept saying he had diamond skin. So it's bulletproof, man. Bullets bounce right off. And he was able to do something with light and turn himself invisible. It was kind of neat. but they took him down with electrical current. They could knock him out with that, which doesn't make sense if his skin is actually made of diamond because it's a non-conductor. Right? We'll find out later maybe if his skin was made of graphite, right? That would be a whole different scenario. But, you know, as a chemist, it kind of messes you up when you're watching movies and reading things. You're like going, that doesn't make a whole lot of sense. You know, you shouldn't be tossing around that gold statue like it's a beach ball because that's going to weigh like 50 or 60 pounds. Right? That's a lot of fun. Or having diamond skin, right? That would be a non-conductor. And of course, it's going to be very insoluble. There's no way water or other common solvents are going to touch diamond. Cool stuff, and a lot of neat industrial applications for diamond. And if you're into the beautifulness of it as jewelry, I remember when I was buying a diamond for a wedding ring for my wife, I was looking into that. What was it? That was a long time ago. All the C's cut, clarity. I can't remember cost. Maybe that was one of them. But you know, looking at little impurities in the diamond, right? If you can see the little black specks, you know, not good. It reduces the price. So if you want it nice and brilliant, you know, and shiny, it's going to cost you a bit more. But there are some impurities that can get in there that give it, you know, like a pinkish color or something like that. It's kind of neat. More geology than I want to get into. I want to get into graphite, but diamond is really, really cool. Let's take a look at another allotrope of carbon called graphite, which you probably, like I said, use every single day. Now, we call it pencil lead. It's not lead. It's carbon. It's graphite. I think it might be mixed in with some clay or something like that. But that's one of the allotropes that we use if you're using, unless you write on your computer all the time. But if you're doing it on paper, boom, that's a common use. It's used a lot of lubricants and stuff, too. We'll talk about why. So how's the bonding different in graphite versus diamond? Now remember, diamond had those strong covalent bonds between carbon atoms in 3 dimensions. Graphite's in 2 dimensions. So those strong covalent bonds only occur in 2 dimensions. Now, so picture a hexagon, right? You probably remember benzene, which had the alternating single and double bonds, but there's no double bonds here. So you've got hexagon attached to hexagon attached to hexagon in a sheet. So imagine you've got a 2-dimensional sheet of hexagon rings, right? Kind of like chicken wire. We call that a graphene sheet, right? So an extended network of really strong covalent bonds between carbon atoms in hexagons connected in a 2-dimensional sheet. Now imagine you have a whole bunch of these graphene sheets stacked one on the other. Right? One over the other. And so what happens, you have these graphene sheets with these very weak London dispersion forces between them. That's one of the keys. Right? So you got this sp2 bonding within, you know, in between here. So you got these sp2, right? There's another one coming off this way. So you get those 3 covalent bonds. And you got this p orbital, right, floating around. So the electrons are actually shared between those p orbitals, so they're delocalized. A little bit different. That's going to make graphite a conductor of electricity. That's how it's different from diamond, because in diamond they're stuck because of the sp3 bonding. So very weak London dispersion forces. You know, it gets around 335 picometers between layers. Here's a model of it, right? So here, can you see the hexagons there? Hexagons, and that forms a layer. There's your graphene sheet, right? And then you got another one here, and that just continues on with these weak little London dispersion forces between them with about the 335 picometers. What makes this fascinating for the properties is good luck trying to pull these apart. Those are strong covalent bonds, right? But these are weak intermolecular forces. Couldn't we just like pop that off? It wouldn't take a lot to break that. Like if I took this pencil, placed it on a piece of paper, right? And went, ugh, right? What happens is when you apply that lowest level, when you apply the pressure and you go, the pencil slides over, leaving that one layer of graphite on there, right? So you can peel off the individual layers, and sooner or later the entire pencil will wear down. It's kind of cool, right? Wouldn't that make a good lubricant too? That moves around, right? So you'll see graphite or blends of graphite with other species. Sometimes it's dry, but usually it's mixed in with oils or something. Makes a wonderful, wonderful lubricant in a lot of scenarios. So just kind of some special bonding there. So we'll list some properties on the next board, but I just wanted to give you an idea how different this allotrope is versus diamond. Okay. And when we get to thermodynamics, we'll talk about graphite's actually more stable than diamond. So over time, diamond turns into graphite. Oh! So when we get into kinetics, how fast things occur, you don't be worried that your diamonds are going to be worthless pieces of graphite over your lifetime. It takes like billions of years. It will happen in time, but not during your lifetime. So your diamonds are okay. So let's look at some, I'll relist those properties of graphite on the next board. Graphite's really cool. That structure is really cool. All right, let's take a look at these properties, just kind of sum them up for graphite again. Remember, you've got those graphene sheets that can move and slide, makes it a great lubricant, right? And used as pencil lead, right? Which we've used every day of our lives, most of us. And again, those, because of that weird sp2 bonding within the sheets and those p orbitals, those unused p orbitals dangling, allows the electrons to be delocalized so they can move. So if you put electrical current into it, those electrons can flow, making graphite a great electrical conductor. Right on. So what I want to do is look at a couple of the newer allotropes of carbon. You've probably heard of carbon nanotubes, nanotechnology, buckyballs, things like that. Let's just do a brief look at those real quick. Maybe a quick look at SiO2 is another network covalent solid. We'll polish off this video. Now, let's take a look at this other allotrope you've probably heard of, carbon nanotubes. Imagine, like in graphite, you have those graphene sheets, right? Those two-dimensional ones, but instead of stacking them one on top of another, imagine you roll it, right? So let's take one of those sheets, I'll take my bond energies, and just do this. Oh, like chicken wire. It has a kind of a natural tendency to do this. You'll see it go boing. Oh, whoa, right? And if you cap off the ends, you get a carbon nanotube. Look at that. This is just the base, so it stands up. So get rid of that. See, do you see the hexagons there? The two-dimensional graphene sheet rolled up. Woo! You get like a carbon nanotube, right? Really small diameter, maybe a couple hundred nanometers long, maybe even the micron region long. These little tiny, almost like wires. Oh, so many cool potential uses in the world of nanotechnology, which we're not going to get into, but let your brain just go with creative applications of this stuff. So take that 2D graphene sheet and just roll it up like chicken wire. Boop, boop, boop. You got yourself carbon nanotube. Neato. Well, remember, this has great electrical conductivity. These have amazing properties, mechanical, structural, electrical properties. Woo! So tensile strength. So kind of like you ever heard of like the great tensile strength of spider webs? Try this, right? So you get crazy applications like, well, what if I could get one of these long enough or wrap them up like a braid and have them go all the way up to the moon? I could create like a space elevator made of carbon nanotubes, right? I mean, things we do today, when I was a kid reading science fiction, that stuff didn't exist, and it exists today in some form. So 40, 50 years ago, we were like, there's no way this is possible. And it is. Who's to say that can't happen, right? Hopefully somebody invents teleportation. Please, somebody invent teleportation so I don't have to commute. Right? Boop, boop, hey, my work, hey, boop, boop. I can see my family. Again, great electrical conductors. Can you see how this would immediately go towards nanowires for little tiny computer chips? You think they're small today? Imagine if we could use these as wires instead of copper. Boom! Right on. Structural reinforcement. I think they do that now instead of like rebar, right? For concrete. You ever see in concrete, you see the little metal bars, the rebar. What if we used carbon nanotube things? I don't know. I'm not an engineer, but you could think about it. A lot of cool stuff. I'm not going to write this as a separate thing, but another allotrope you'll see, which isn't really a network covalent solid per se, is you ever heard of buckyballs? They discovered these, I think, back when I was in high school, like 85-ish, something like that. You get like a soccer. Imagine a soccer ball where all the lines intersect is where a carbon atom would be. So you get these hexagons. See the pentagon there and the hexagon there. I think there's 60 carbons in here. I forget the shape of it. I don't even want to attempt the shape, right? But imagine a hollow soccer ball made of carbon atoms. That's called a buckyball or a Buckminster fullerene. Potential applications in nanotechnology would be great, because what if you could get something in the middle in there, right? maybe some kind of medical compound in there, and you can send these through your bloodstream like little sentinels, and they can find like individual cancer cells. And once it hits it, put something on the end here, dock it on there, it releases the payload, so you can do a cancer treatment that doesn't kill all the good cells around it. Wouldn't that be cool? Right? Hydrogen storage, man, if you could get each of these carbons, right, bonding to hydrogen, you could, look at possible fuel cells or hydrogen cars, things like that, hydrogen fueled vehicles, where you don't have liquid or gas phase hydrogen. That's not good. I mean, think of the applications you could have for buckyballs and carbon nanotubes. So cool. All right. So let's look at one more real quick. Let's look at quartz and see how that can be looked at as a network covalent solid as well. This one's for my son. All right, so if you're into geology, this is a way oversimplification, but silica, or silicon dioxide, the way the bonding, it's obviously not a molecule of SiO2, right? But there's a lot of different forms of quartz. But if you look at how silicon works, it's right below carbon, right? If you have carbon, silicon's right below it on the periodic table. So you're like, okay, bonding is... And it's somewhat similar. It's just silicon can't bond to itself like carbon can in a three-dimensional network. But if you alternate it with oxygens, silicon, oxygen, silicon, oxygen, silicon, oxygen, oh, interesting things can happen. So like for example, take carbon. It's got that three-dimensional network of tetrahedrons. If you replaced every other atom with silicon, you'd have silicon carbide. Super duper hard, almost not as hard as diamond, but it's up there. But now let's do tetrahedron. See the silicon here? And if you get a tetrahedron, I couldn't draw it. I don't have enough room on the board here. But if you draw a tetrahedron to all the oxygens and then have the silicon oxygen silicon bridge, tetrahedral oxygens, and then go off in 3 dimensions, you get that silica bonding network, and you get this really, really hard, cool stuff. And then if you get, metallic impurities in there, you can get cool different colors in there, all these different kinds of minerals. Fascinating. So again, in chemistry, we're not going to deal with network covalent solids that often unless you go into, some kind of nanotechnology research with carbon nanotubes, or, maybe you're looking at diamond and graphite stuff for industrial uses or applications, maybe. But other than that, we're not going to be dealing with it too much. So this video is just kind of an isolated one, kind of for fun. Yay! All right, so what we're going to do, we're going to get into the last part of the solids here, the metallic solids. We're going to do several videos on there with the ultimate goal of being able to look at a metallic solid like copper or, whatever, tungsten, something like that, iron, and look at the lattice, the crystal lattice on an atomic level. Look at where we're going to look into what are called unit cells. And based on some geometry, brush up on geometry, we're going to be able to calculate, not measure. We can measure the density of metals pretty easily. Just measure the mass and the volume in lab. You're good to go experimentally. But we're going to be able to theoretically calculate the density of solids based on how the atoms pack and look in what are called these unit cells. That's our ultimate goal. Let's get into it.